Okay.
Let's jump into it. Like I said, we're going to do a couple more examples from the handout here. Which again, remember, I put an electronic version online on the class webpage, so if you lose it, you can get it back. Or if you're using like a tablet or something, you can pull it up. So we kind of already know the theory, we're just going to apply it to some more examples, so we'll jump right into it. Let's just begin. Let's jump ahead to problem 3. Yes, it was on purpose. We're going to 3. What? You're going to skip that for the notes. Yep, let's do that. So a company is considering 2 insurance plans, and these are infos on the insurance plans. So we have policy A, where for each unit bought, you get $10,000 in fire and theft insurance, $180,000 in liability, and it costs $50 per month or whatever. For policy B, $15,000 for fire and theft, $120,000 for liability, and its premium is $40 per month, or whatever time you're paying your insurance bill. So, a company wants to actually get $300,000 in fire and theft insurance, at least, and at least $3 million in liability insurance. How many units of each plan should be purchased in order to minimize the cost of the premiums? And what is the minimum cost? It turns out that this is a linear programming problem. So, usually how we're going to start is we're going to want to describe our variables. So, let X be the number of units of plan A. So Y equals number of units of policy. All right, what do we want? What is our objective? We want to minimize something. Minimize what?
Premiums.
Premium cost, right? We want to minimize the cost of the premiums. So we want to minimize cost. What is the cost here? Yeah.
50x plus 40y.
Right, so it's 50 per unit of A and 40 per unit of B. So it's going to be 50x plus 40y. This is the function. It is a linear function. It's just a linear program is going to work. What are the restrictions, the constraints here in terms of these variables? Yeah.
What was it? X is greater than or equal to 0, y is greater than 0.
Yeah, those are automatic because you're obviously going to be buying some of them. Okay, what else?
You need at least 300,000 of fire and theft.
Okay, so how do we describe that? For fire and theft, we need 300,000. What are we getting for fire and theft?
10,000 x plus 15,000 y is greater than or equal to 300,000.
Okay, so that's one thing. That's what we require for the fire and theft. And we also have liability insurance. And by a similar idea, we can get 180,000 for each unit of A that is purchased, and 120,000 for each unit of B that is purchased, and we want at least 3 million. 6 zeros. That's it. So we want to actually minimize this function in the presence of these constraints. This is a linear programming problem. So that is how we set up a problem. We start by calling our variables, defining our variables, the x and the y, which we're only going to be doing 2 dimensions, so it's always going to be 2 variables that you have to worry about. And then you pretty much describe everything that's going on in the problem in terms of x and y. And you figure out the thing that's important to you in terms of x and y, and you want to minimize that thing in terms of these things. So once you have a linear objective function and linear inequality constraints, this gives you a linear programming problem. So what we will do is we would first find the feasible region. So we are going to actually sketch all of these guys and find out the solution in terms of a region. So that's going to be, that's your x equals 0, this is your y equals 0, and I know I want to be to the right of this and above that, so it's going to be in the first quadrant. And yeah, now we're going to plot each of these lines. So plotting this one, remember you plug in one of them equals 0 at a time. So if I plug in y equals 0, I would get x equals what? Like 30, right? Huh?
Yes.
Yes. So I'm going to mark 30 here. If I plug in x equals 0, I'll get y equals what? 20. There's the thousands cancel, and then 15 into 30 goes 3 times, so that's 20. Okay? So mark that, that's 20. And let's do a straight line. So this is the fire set line. I'm not going to write out that full equation here. We're going to do the same thing with the other line. So plug in y equals 0, I would get x equals what? 3 million divided by 180,000. What do we get here? 16 and 2/3.
Yeah.
So let's put that over here. 16 and 2/3, or 16.67 rounded. And if I plug in x equals 0, solve for the y, 25 even. So here we get 25. And that's it. Now we want to be greater than or equal to both of these. If I solve for the y, it means I need to be on top of both of these lines. I need to be on top of this line, and at the same time on top of that line. So that gives us an unbounded feasible region. So there's no limit to what you could spend in insurance, of course. But we actually want to find the minimum. Notice that this guy, if I were to set this equal to a value and sketch it as a line, it will have negative slope. So the line is here. I can shift it up as long as I want to. There will be no maximum. But shifting it down as much as I can, there will actually be a limit before I leave the feasible region. Therefore, the points of interest are going to be this, because that's on the boundary line at the corner, this, and this. So we have that theorem that tells us the solution to a linear programming problem will occur on the boundary or at a corner point as long as an answer exists. Here a maximum doesn't exist, but a minimum does, and the minimum is what we want. The minimum will be at one of these points. This point here is pretty obvious, 0.25, because that's the y-intercept. This point here is also obvious, that's 30, 0. This point we need to find. So that amounts to you solving a system of equations.
Is there a reason you didn't plot the cost function?
We never plot the cost function.
No, you know.
Yeah, you only plot the constraints. Right. The cost function comes in when you're doing a test, when you're going to do that table. Right. So you only plot the constraints and find the feasible region. thing is the cost function isn't really a line, it's a variable. So we don't really know where that line should be in the first place anyway. But let's actually find that point right here. That's going to be the intersection of these two, 10,000 x, 50,000 y equals 300, 123, and 180,000 x plus 120,000 y equals 3, 1, 2, 3, 4, 5, 6. I can reduce these. I can divide through by 10,000.
Wait, isn't it only 15,000 Y in the first one?
Yeah.
Okay, so yes, so I can't divide through by 10,000, I can divide through by 1,000. So, and then I can divide further by 5. 5 into this goes 2 times, 5 into that goes 3 times, and 5 into that goes 60 times. I can divide this by 10,000. And I can go further into that by 3s or 6s. 6 into 18 goes 3 times, 6 into that goes 2 times, 6 into this goes 50 times. So these are the 2 lines that I care about. Let's do the elimination method right here. Multiply the top one by 3. Multiply the bottom one by 2. Then I can take the equation 1 minus equation 2. So equation 1 is equation 2. 1 minus 2. So I will have 5y equals 80. In other words, your y would be equal to what? And then I would have 3x, let's use this one, plus 2 times 16, it's going to be 32, it's going to be equal to 50. So 3x is going to be 50 minus 32, which is going to be what? 18. So that means your x is 6. So this coordinate here is actually 6, 16. And so now, what I'm going to do is I'm going to test those points. So this is where we bring in the objective function. So we're going to have x, we're going to have y, and we're going to have the possibility for the f. 50x plus 40y. So possibilities are no units of A, but buy 25 units of B. Or I can buy 6 units of A and 16 units of B. Or I can buy 30 units of A and no units of B. And then I'm going to plug that into here. So 50 times 0 plus 40 times 25 is going to be what? Huh? 1,000. 50 times 6 plus 40 times 16. Huh? And 50 times 30? Yeah, and that's going to be the winner. That's the cheapest premium. So under these conditions, with those premium values, that's the best price to buy pay for your insurance. This means the minimum premium cost. $940 to obtain at least 300,000 in theft and fire and 3 million in liability, which occurs for 6 units of policy A and 16 units of policy B. That's your answer. That's the best situation for the people buying the insurance. Yeah.
If you have a situation like this where you're trying to find the minimum, is it ever not the point in the middle?
Yeah, depends.
Even if you only have 2 lines? Even if you only have 2 lines?
Yeah, it's possible. It depends on what this function looks like. So for example, if there was a subtraction on one of these, try hitting one of the 0 points where you're subtracting 0 immediately or something.
Last class, did you solve the system of equations by using matrices?
Yeah.
Yeah?
For a linear programming problem, I actually don't pretty care. Do whatever's good as good. You do need to know row reduction for other things. So last class I just did it just to get some more practice in. Do it until you're used to it. But when linear programming is the goal, I don't particularly care how much you solve system. This is just one small part in a big problem. But yeah, that's the run through of the problem. Define your variables. You're going to figure out your objectives, set up your constraints. You're going to sketch them. Find all the corner points because your answer is going to be there. To find the corner points, you'll need to do systems of equations. Do that whichever way you're quickest, and then test all the values you find and make your conclusion. Any other questions? Let's do it again. Plane carrying food and water to a resort island can carry a maximum of 30,000 pounds. It is also limited in space. It can carry no more than 525 cubic feet of stuff. Each container of water weighs 60 pounds. Let's start actually writing some of this stuff down so we don't get confused. Looks like we want to talk about water and food and so that their weight and the space that they take up. And let's talk about the max that we can handle. So let's do that. Alright, so water weighs 60 pounds per unit. And takes up 1 cubic foot of space. So this is per unit, and this is cubic foot of space. Okay, each container of food weighs 150 pounds. Take up 5 cubic feet of space. Now our plane can carry a total of 30,000 pounds and 525 cubic units of space. Okay. All right. Hotels on the island will buy the food for $16 a pound. This is per pound. So let's look at this here. Cost per pound. Okay, so the hotel is going to buy the food for $16 per pound and the water for $5 per pound. Water. Okay, what is the optimum number of containers of each item that will maximize the revenue generated by the plane? What is the max revenue? And they also told us let X represent the number of food containers, calling this X, and Y represent the number of water containers without water. Okay, so we do have, we know what our goal is here. The objective is to maximize something. Maximize revenue. How do we compute revenue? What's the revenue going to be?
Well, which makes sense.
Right, which basically is the number of things you're selling times the price for each thing. So what's the revenue generated by carrying the food and water here?
5Y plus 16X.
16x plus 5y is going to be the amount of money that plane makes for each trip. Right, for every container of food, which is x, we get $16. For every container of water, which is y, we get $5. So 16x plus 5y is the amount of money that we'll make by that one trip. Now we have our constraints to worry about. And what are the constraints?
Can't go above 30,000.
Okay, so in weight, we have constraints on the weight and the size. Basically, weight and volume are constraints here. So the weight must be less than 30,000. And the volume must be less than or equal to 525. So the weight is, well, it's the weight of the water plus the weight of the food. And the weight of the water is going to be
60Y.
60y and 150x. So that's the first one. And in space, the water is going to be 1y, and the food is going to be 5x. And again, here, these are automatic. You can't bring negative units of food. We're bringing nothing or yeah. Basically, if we can make the most money by not giving them any water, we're going to do it. Like, yeah, you don't have water. Maximizing revenue is the only concern. I don't. Okay, so now we're going to start sketching these guys. And yeah, problems 3 and 4, why I wanted to make sure I get through those two, because on a test, the level of difficulty of a linear program problem that I'll ask you is probably going to be around this level. Maybe you'll have one more line, but as you can see, when we did problem 1, that was crazy. There were like lines all over the place, we weren't sure where we're It's not going to usually be that big. I'll give you like 2 lines, maybe 3 if I'm feeling a little bit crazy. But the level of difficulty is going to feel more like problems 3 and 4. More so than one or 2. Yeah, so let's go in and get this done. So our y, let's start here. What is, so if I plug in y equals 0, solve for x, what do I get? Huh?
200.
Divide by 10.
200 is 200.
It's 200.
That's 200.
I put it in the calculator. I forget these people. I can't trust them. Okay, so let's put that at 200. I don't know where it is. A good place to write this. Okay, so, and the y, it'll give you 500.
Wait, X
Wait,
is
wait,
200.
X is 200. X is 200. And the y,
105. Oh, wait.
for this one.
5.
So the 30,000 divided by 60. 500?
Yeah.
Let's make that 500. And so now I'm going to connect these guys. So that's describing the weight here. We're gonna do the same thing over here. So this one, the weight is 525. That's easy to see here. That's just one y. And the x is going to be 525 divided by 5.
105.
What?
105.
Yeah.
105. So that's going to be halfway here. 105. That's 105. Okay. And that's talking about the volume that we have. Okay, so now what? Oh, we also have the x equals 0 and the y equals 0. And so I know I want to be to the right of this guy, above this guy, and I want to be below this guy, and at the same time below this guy. So where does that leave us? Like here. That satisfies all the requirements here. So I'm pretty sure doing nothing is not going to be the answer, but that's actually a corner point. What's the minimum amount of money I could make on this? Nothing. Just don't do anything. Stay home. Or you can 0 to 500. This one here is, so yeah, we can give them, the y was the water. So we can actually say, don't give them any food, give them 500 units of water. Or we can be like, okay, give them 105 pounds of food but no water. Let's figure it out. You're on an island, come on, they probably can get water anyway. There's tons of water. That point you need to work out. So it's just going to come down to this guy, which so I reduced this by 10, it's just writing it down. And we can probably go even further. I can take 3's into everything here. 3 to that goes 5x, 3 to that goes 2, 3 to that goes 1,000. So that's 2, that's 1. Let's take 2 minus 1. So that minus that equals 11. That's 1,000 minus 525, is that 475? And so our 5x plus 475 should give us 525. So 5x is going to be 50. Is that right? And so that's what we are here. 10 units of food and 475 units of water. And now what we're going to do is we're just going to test all these points in this function, 16x plus 5y. Zero, you know that's not going to be it. 105 and 0. So that's going to give us 0. This. Huh? 2,5? 2,400? Fine, they get both food and water, these people. lucky them. That's actually better for me. So, highest revenue. $2,535 per trip with 10 units, pounds or whatever of food. And 475 units, pounds or whatever of water. So that's the best thing to do. And one thing you could notice here, well, I didn't check actually what the max capacity is. I don't know if the plane is actually even full at that point, but that's the answer. For maximum revenue, that's what we do. Which is the starting point. Hopefully, as did I even talk about part B to problem 1? Did I talk about part B to problem 1? Oh, so I was gonna like refer to that. As problem 1 shows. The math is the starting point. This kind of tells you where you should kind of be looking for the answer. But of course, if the resort actually makes requests that are kind of different from these numbers, you fulfill the request, right? You don't just, well, that's not good enough for me, forget them. So sometimes the numbers don't tell the full picture. So in problem 1, part B, the idea there, I thought I had mentioned, one thing you could have noticed, you were required to use 2 units of food B. But the best situation used 4. So the idea was, what was something that you could do to make this situation even better? And the math itself wasn't what actually gave you the answer there. It just comes down to you actually thinking as a person, interacting with other people in the world. And probably a good idea to do in this situation is to actually renegotiate the contract. Renegotiate. The contract. So basically you got a good price on B because you negotiated a contract with this guy. I am buying at least 2 units of your product. Guaranteed, every time I serve a meal, give me a deal. But through going through the calculations, you realize it's actually better for you to serve 4 units. So what you can do is you can go to this guy and be like, I'm gonna double my order, right? Every time I make an order, I'm doubling my order. Cut me a better deal, right? You will actually work out more economically for yourself. And at the same time, the guy who's selling the food units of B, he also gets to sell more of his products and make a profit. You end up in kind of a win-win situation if you can get that to work. That was kind of the idea. So the math, yes, it's powerful, but it's not everything. Sometimes you just have to remember there are other people around. It's not just about the numbers all the time. The great thing is, if the numbers, you can get it to work out in life to follow the numbers, that's awesome. But otherwise, you just try to get as close as you can. I wanted to try 2 on your own. There's a little trick in problem 2. I want to see how you guys actually deal with it. So next time you can tell me what answers you got, and I can tell you if they sound kosher. I'm not sure what I can do in 5 minutes, but the next topic is going to be set theory. We're going to talk about set theory. Come again?
Are we doing 2 right now?
No, you go do two.
Oh,
Next time I see you guys is what, Tuesday? Yeah, tell me on Tuesday what you got. We're gonna do all that, very fun. I wanted to actually at least start set theory because of my other class is gonna start pretty soon. We're gonna get far.
Is that on the midterm?
I think it is on top of it. Yes. So we're not gonna do this in all its glory. I'll probably talk about that some other time when we have more time. Because I did set theory as an undergrad. I took a graduate course in set theory, and it was crazy to say the least. I'll probably tell you the story next time. It was one of my life-defining moments. It's one of those things in my life that made me who I am today. It gets really crazy. We're not going to go anything too crazy though. So we'll start out with stuff like Venn diagrams. Everyone likes Venn diagrams and things of that sort. But everything I'm going to teach you in set theory, it is for the goal of helping us be better at probability. Probability is going to be a big topic that we're going to talk about. As business majors, you are going to take a statistics class separately. So I'm not going to talk about statistics in the class, but we are going to talk about probability. And it starts with a good idea of what sets are and how they behave. Let me tell you a definition. A set is an unordered collection of objects called the elements or members of the set. And in stating these members, repetition is not allowed. So, an unordered collection of objects where repetition is not allowed, we call this a set. There are many things in life that you can talk about in terms of sets. So for example, let's say I am the owner of an Airbnb and I'm talking about all the amenities that you can have if you rent my house. I can describe this mathematically as a set. You get Wi-Fi, you get heat, you get hot water, you get all these things. Now, there's no inherent order in me listing these things. I mean, some people like Wi-Fi more than hot water or whatever, but there's no inherent order. Also, I can't really tell you this with repeats. I can't be like, I have Wi-Fi. I have Wi-Fi. You're going to just be like, no, you just said the same thing twice. That's one thing. It doesn't count to repeat. It doesn't make sense to repeat. Now, whenever you're in a situation where you're talking about a collection of things, it doesn't make sense for you to repeat yourself, and there's no inherent order. You use a set. Okay? The notation for sets. One, we can name them, usually with uppercase letters, but we often use like these squiggly brackets. So I can have a set called with the elements A, B, C, D, E, F. Okay? That's the, for example, that is a set. It has 6 elements in it. Right? Or I can say something like A, B, C, dot, 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 F. We can use ellipses to indicate that there's an obvious pattern that you can follow from this point to that point. Or I can say something like X such that X is a letter of the alphabet. Between A and F inclusive. Right? So there are various ways you can actually talk about a set. You can list all the members. You can list members, but maybe there are so many that you can use ellipses to kind of help you out when you can write them down in a certain pattern. Or you can describe them by a property, and you can just say, I'm calling the objects this name, this means such that, or on this condition that this property is fulfilled. This is called the roster method of talking about a set. Use those curly brackets. And again, here's another definition. Two sets A, B are, we call them equal if they have precisely the same elements. So if my A is A, B, C, D, E, F, and my B is B, B, A, E, F, D, C, then, yes, B is repeated. Did I get everyone here? I missed the E. So, example, we can write A equals B for these two sets. They're the same set. Yes, this one repeats, and it mixes up the order of the things, but we don't care. Sets, we don't care about order, we don't care about repetition. These two guys are the same for all intents and purposes. What if we do care about order and repetition? There's another kind of object that we can use. A tuple is an ordered collection. Where repetition is allowed. Notation for tuples. They look like coordinates. So I can also give them a name, and I just use regular parentheses, and I can list the elements here. Order matters and repetitions are allowed. I want you to realize that this is not the same as me putting the B first, then the A. It is also not the same as me repeating the A twice and then putting everyone else. This kind of object cares about repetition, and it cares about the order. There is a first element, and a second element, and a third element, and these positions aren't malleable, right? So, one thing that you might think of as representing a tuple, to give you another example, your grades in the class, for example. You would have like test 1 gives you a certain grade, and test 2 gives you another grade, and the final gives you another grade, right? These things, the order matters. So if I put a number here, I get a 95 here, and a 95 here, and say an 89 here. That is, it matters that the 95 shows up twice. That tells you got the same grade on 2 different tests. If we were to put this in a set, the information gets lost, and then you don't even know which grade corresponds to which test. So there are situations in which order and repetition matter. There are situations in which order and repetition does not matter. And these two things is going to be the crux of probability. People have problems in probability because they don't know the difference between sets and tuples for different situations. A lot of our time is going to be spent figuring out when a set is useful, when a tuple is useful, and it will tell us what methods we can use.
Is repetition out of the tuple? Or?
Yes, repetition is allowed. So I can put an A and an A, and I'm not supposed to erase one of them.
But how is that not?
Oh, because this tuple has 1, 2, 3, 4, 5, 6
Oh,
things,
okay.
that only has 5 things. Alright. We will build on that next time.
I'll take you, but I have like, what you call it?